Okay, so let's get started. Uh, Jendi has an announcement to make. So about a new club. So why don't we let her talk for a few minutes and then we'll begin the class.
Okay. So hi everyone. My name is Jendi and I'm a part of the Developer Student Club chapter at Stony Brook. So I'm here today to just give a little info session about our club, what we do, and what events we'll be hosting this year. Okay, so first of all, what is DSC SBU? So DSC is basically a worldwide community of students interested in Google developer technologies. We host events, workshops, guest speakers, and maybe even a team challenge to better educate students at Stony Brook about the different frameworks and languages to become more industry ready. Here are some of the examples of the workshops that we'll be hosting this year, including Flutter, Angular, Firebase, Google Cloud Platform, Android development, and TensorFlow. Okay, and one specific event I would like to tell you guys about today is one that will be hosted this weekend, Saturday, September 26th at 1 p.m. EST. So we'll be hosting the Cloud Hero Data and Machine Learning Workshop. And during this workshop, you can get familiar with the key Google Cloud Platform solutions and learn about the fundamental tools and capabilities of Google Cloud. Okay. Also, fun fact, after completing all the labs in this event, you're eligible to receive a Google Cloud skill badge that you can show off to recruiters. So hope to see y'all there. And just some general information about DSC is that we'll be sending out announcements about upcoming events through our social media, email, website, and Discord. So make sure to stay connected. And this year, all of the workshops will be held virtually on Zoom because of COVID. So you can just hop into an event in the comfort of your own home. And everyone is welcome to join as a member of DSC. You don't have to be a CS major to join. So feel free to grab your friends and learn something new over the weekend. And this is the link tree, which I will also be sending in the chat of Zoom. So this is where you can see all of our social media links, websites, mailing list, and Discord server. And if you have any more questions, feel free to reach out to me, the email, or the Discord server. And thank you again, Professor, for letting me talk about the club. And that is all. Okay.
So thank you, Jendi. It sounds like a very interesting club. So I hope some of you look it up and see what they have to offer. So let's pick up from where we left off. So I have okay now. This is not it. Give me a minute. I'm having some issues. Let's see whether I have the right version here. Okay, good. I have the right version. Okay, good. So okay, very good. So let's pick up from where we left off in the last lecture, right? So we started talking about operations on relations and about graphs. Can more of you turn on your cameras? Okay, I'll wait for some more time. Let me see more of you turn on the camera so that I can see more of the people in the class. Okay, good. Getting there. Very good. Very good. Thank you. So, so let's see. So we started. Let's just review one or two things that we said in the last lecture, and then continue from there. Okay. So the first concept I introduced is that of composition of relations, right? So we can think of it, pictorially like this. So you have the sets A, and you have the set B, and you have the set C, and there are arrows between A and B that describes the relation R, and then there are arrows between B and C that describe the relation S. Okay, and so let's say we have A, B, C, right? And maybe there is 1, 2, 3, 4, and then you have A, and then let's say we have capital letters here. Okay, A, B, C, D, and let's say right. So we have so now if you take the composition of these two relations, okay, then just give me a second. Okay, so if you take the composition, that means what that means pictorially is that you go from A to B using one of those arrows, and then you go from B to C using the arrow from the point that you reached, right? So we can say in this particular example, A are composed with S. So can you answer what should go here? A is related to what point? The composition. Someone can just answer without lifting their hands. So A is, if you start from A, you take the relation R, one of the edges in R, and then one of the edges in S. Where would you arrive at?
Capital A?
Capital A. Okay. Can you arrive anywhere else? No, right? So what about lowercase b? That'll take you to?
Still capital A?
Will it take you somewhere else as well?
Capital B also?
Okay, so we see two paths here, right? So you can go from B to number 3, and from number 3 you can go to A. So we have that. And then we also have another path. So from B you can go to number 2. Number 2 will take you to B. So you can do that. Okay, so that's how composition works. Okay, so we can understand composition in terms of this kind of a picture, but sometimes you can understand it if you understand R, not so much in terms of pictures, but in terms of what it means, right? So let's say we define an R from n to n as follows, right? So A or B if A Okay, A equals B plus or minus 1. Okay, so let's say that is when we will say A and B are related. Okay, maybe I'll just make my life easier by just making it a, you know, right? So that I have both positive and negative numbers, and that kind of simplifies the understanding. And let's say I have S, which also takes Z to Z, right? And I say A or B if A equals B plus or minus 2. Okay, so now can you tell me should say if and only if. Okay, so what is the composition of R and S in this case? If someone can lift their hand, and then I'll. Right, R says, R connects to every connects a number to itself, a number that's one larger by 1 and large and no, I'm sorry, it doesn't connect it to itself. It is because we say plus or minus 1. So for instance, if you take A to be 5, then A will have an arrow to 4 and 6, right? So that's what R is, right? Now, if you look at S, and I made a mistake here. So when I make a mistake, you can point out, because often these mistakes make it very difficult to understand what's going on. So here, a number, let's say 10, will have an arrow to 12 and 8, right? So when you compose R and S, what are you going to get? It's okay to be wrong, right? Go ahead and take a guess. Yeah, go ahead, Brian. I don't know why.
Be A equals B plus or minus 3 or B plus or minus 1.
Okay. Right. So what's going to happen is that let me, yeah, you're right. Why don't we first make the example okay, a little bit simpler, and let's just say, instead of that, let's just say, right. So now why don't you answer the question again, and then we'll go back to the more complex problem.
Wait, sorry, do you want me to say what I said?
Yeah, in this case, right? If S is just B equal, it's just plus 2.
Oh, okay. Then it would be A equals B plus 3 or B minus 1.
Right. So composition, so we can see again with an example, right? To first give us an idea what's going on. Let's take, A. So A is connecting to A minus 1 or A plus 1. That is this relation R, right? So let me just make a line there so I don't get confused. So this relation is going to connect A with a number that's larger or smaller by 1. So it's going to connect to A minus 1 or A plus 1. And then from A minus 1, you can go, the second relation S is going to connect to a number that is smaller by 2, right? A equals B plus 2. Right, so this is going to be A minus 3, right? And from here, S will connect to b minus 1. I'm sorry, a minus 1. Right? So this is our R edge, and these are our S edges, right? So the S simply goes to a number, that's smaller by 2. Okay, so okay, so let me try this again, because I think I feel that I don't recognize enough faces
Should it
understanding
be
this. So let me just change the example
equals-
a little bit, which will make this a little bit easier to follow. Okay.
I have a question.
Yeah.
Should it be A equals B plus 1?
Let's work through the example again, because I already erased it. So let me just create myself a little bit more room so I, don't. Okay. So okay, so let me also define it. Let's start all over. Okay, let's start with a clean slate. Okay, so let's say R from Z to Z. Okay, A, R, B, if and only if A plus 1 equal to B, or A minus 1 equal to B. Okay, so similarly, let's define S going to from Z to Z as A, R, B, if and only if okay.
Wait,
So-
what does
I'm sorry?
what does ARB mean?
A or B means A has a relation to B,
Okay.
right? So that is the ASB again, okay? So, so we say that A and B are related if one of these conditions holds. A and B are related by R if one of these conditions holds. A and B are related by S if this relationship holds. So now we can try to understand what the composition means by sort of trying to sketch out what happens. We start from A, right? So this condition will connect us to A plus 1. This condition will connect us to A minus 1. So this is what R does, right? So now we can apply S. S is going to connect each of these points to a number that's higher by 2. So that's just going to be A plus 3 and A minus 1. If you add 2 to that, you'll get A plus 1. Okay. So is that better?
Yeah.
Okay, good. So so again, your intuition, of course, looking at this immediately tells you, hey, yeah, okay, I'm adding 1 and then I'm adding 2. Therefore, I should, in effect, have added 3. Or I'm adding minus 1 and then I'm adding 2, which means effectively added 1. Okay. So now let's go back to the slightly more complex version I had, which was right? A plus 2 equals B, or A minus 2 equals B. Okay. So now what are you going to get? So A are composed with S, B, if what condition? Right. So we are going to have, instead of just going to plus 2, we are also going to minus 2. Therefore, you'll go to A minus 1 there, right? And again, A minus 1, you can either add 2 or subtract 2. So we will have A minus 3. right? So you have A R composed with S of B if A equals B plus 1 or okay, I'm sorry. So let's not change the way we are writing this. So right? So you see A minus 1, right? A minus n equal to B, or A plus 3 equal to B, or plus 1 equal to B, or, right? So there are just 4 possibilities. But again, the point is that you need to sort of think about, finding all the elements, right? So, so essentially the way you compute this is you find all the B's to which a given A is related, and then from that B, find all the C's that it is related to, and then all of those are in the composed relation. Okay. Again, we have taken examples of function composition, right? So for instance, if remember, so what's the difference between a relation and a function? What's the difference between a relation and a function? Anybody wants to try answering the question?
For a function, one input can only lead to at most one output.
Right. And then for a relation?
One input can lead to multiple outputs.
Right. So which we, in other words, say it has, a function has, less than or equal to 1 out property, right? So when we draw these arrow graphs, we can say that there can be at most 1 arrow coming out of each point in the case of a function, right? In the case of a relation, you can have multiple arrows coming out of a point. Okay, so this is the only difference between a relation and a function. Okay, it's about whether you have this, at most 1 arrow out property. Okay, but otherwise, functions and relations are very similar. Therefore, whatever intuition we have about, function composition will work for relation composition and vice versa. So if let's say R happens to be a function, right? Again, relation is a generalization of a function, right? So if R happens to be a function which says, AR B if A equals to B, and we say A SB if and only if A equals 4B, then what would be the composition of R and S? Okay, what will be the... Go ahead and answer. It's okay.
Would it be 1/8?
So, right. Let's write that. In other words, the C should be 1/8 of A, right? That was the answer. So, so we can, again, we can think of relations, relational composition in terms of, following these arrows twice the R arrow once and S arrow once, right? So that is the, that's basically the definition of what composition is, because it says, use the R arrow once going from A to B, and then use the S arrow from B to C, right? So that's the definition of relational composition. So that approach will always work, but sometimes we have an understanding of the relations R and S in terms of functions that we understand, such as it is something multiplied by 2 or something squared or something like that, and then we can think of composition in terms of composing those functions, and then you can get the answer more quickly instead of following the arrows here, because following the arrows takes a little bit longer to get to the same conclusion, right? But of course, following the arrow is a sort of a foolproof way that'll always get you to the right answer.
I have a question.
Yeah.
Does it matter if we write it in terms of, like, let's say instead of A equals 2B, can we write 1/2 A equals B?
Yeah. Everything is fine.
All right.
I'm just trying to avoid the confusion, because the first time I wrote down the example, the confusion was, going back from, I said A equals B plus 2, and then everywhere else it had to be A minus 2, and A minus 2 looks different from B plus 2. And so that's why I changed it to be a little bit more consistent, so that people don't have to do this, mental math constantly about plus 2 and minus 2. But yes, we can state this in whichever way we want. It's just a condition, right? Any other questions?
Yeah, I have a question.
Yeah, go on.
For the last example, is A equal to 8C because we have a C in the problem?
Yeah, this is just algebra, right? So in algebra we use variables, and the variables themselves don't mean anything. It's just they stand for something, right? So this is some A, some C, and therefore whatever we say here should also be in terms of this A and C, right?
Okay. Thank you.
Yeah. Okay. Any other questions? Okay. Very good. So let's again, I'm not going to talk about inverse because we had some homework problem on that. And then the next topic we went on to is relations that operate on a single set, right? Already in this example, even though it's 3 sets involving A, B, and C, the example we gave here involved only one set, right? So R and S are in fact relations on Z, right? So when both of these sets are the same, then we call it as a relation on that set, right? So we have a relation from Z to Z. So this is called a relation on Z, okay? And these types of relations are more interesting because things like composition, works out, without having to have sort of a common, this B and this B must be same in order to compose. But if all 3 are same, then you can compose as many times as you want. And so things get, more interesting, and you can study more properties of the, of relations if they go from the same set to itself, right? And it's kind of familiar because when you do your, in math, we talk about functions over real numbers, right? So they go from real numbers to real numbers, right? So we rarely talk about functions that, take real numbers as input and, produce integers as output, right? It's certainly possible, but those are, unusual, whereas most functions will be the ones that start and end in the same set, right? So in the same way for relations, starting and ending in the same set is, advantageous. So that's these kind of relations that start and end in the same set can be expressed using what are called graphs are directed graphs, right? So this is, let's see, why am I having trouble? Okay, so we have some technical issues. Okay. I don't know what happened to my pencil. Maybe it just died on me. Okay, so so we are going to try what's going on here now. It's working. Yeah, it looks like I ran out of luck. I don't know what happened here. Well, I think I can still write with my finger. We'll see how it goes. Okay, so why don't you take a 5-minute break? Okay, so I'll come back in 5 minutes because I wonder whether it ran out of charge. So just take a 5-minute break. I'll come back in a Okay, let's get started again. Yeah, so I don't think my iPad, my pencil quit on me. So I guess we'll see how writing with a finger works. Okay. So relations on a single set can be represented conveniently in the form of a graph where you have things called nodes. Okay, so we have we have example here. So this is a graph, and okay, and then we can say this is, oh, I don't know that. Okay, so maybe if I write large enough, it's okay. So let's see is okay, and then we can have arrows between them. Right, so this is kind of a graph, and so in this case, you have several vertices. In this case, we have labeled them as A, B, C, D, and E. Can I see more of you? And then we have edges which connect two elements that are related. Okay, so the set of nodes here or vertices is denoted as V. Okay, and then the edges are denoted as E, right? So the capital E refers to the set of edges. Okay, and the graph itself consists of this pair, the set of vertices and the set of edges. Okay, now the edges are of the form U comma V, so U and V are vertices. That's what we are saying here. So for instance, there is an arrow going from A to C. So if you write down what are all the edges in this graph, they will be A comma C. Then there is nothing going out of A. So now let's look at B. There is an edge from B to C. Okay, and then there is one from C to D, and then another from C to E, and then finally there is one from D to E, right? So this is the set of edges in this graph, and the set of vertices is A, B, C, D, and E, right? So these A, B, C, D, and E is what V denotes here, and these 5 edges here are the set of edges here. Okay, so we can in the last lecture we tried to represent this graph using our conventional circle diagram, where we have the set V here, and then we have another instance of V, and then we connect A here to C there, and so on, right? And you can go ahead and draw this kind of a picture representing this relation, and you'll find that it's a little bit more clumsy than this one, right? So it's going to look there are going to be a lot more arrows crossing each other over, whereas this type of a representation is much more compact. Okay, So we call this type of representation as a graph, and in particular we call it a directed graph to indicate the fact that the edges have a beginning and an end, and they go in a particular direction. Okay, so so when you have a graph, you one of the concepts related to a graph is its degree. Okay, so the degree, there is this quantity called degree that is associated with every vertex in the graph, and the degree counts either the number of arrows that are coming into the vertex or the number of arrows going out of the vertex, right? So in the case of arrows coming in, we call it as the in degree. When you have arrows going out, then we talk about out degree, right? So let's go back to this example graph we had here. So can you tell me what is the in degree at node C, at vertex C?
2.
Right. So what about vertex A?
0.
Right. So there are 0 arrows coming into A, therefore the in degree is 0, right? So what is the out degree of B?
1.
Right? So there is 1 arrow going out of B. So we say that B's out degree is 1. Okay. And there is a nice little property which says that if you go over the entire graph and add up the in degrees, and then you also go through the entire graph and add up the out degrees, then the two will match. Can someone explain to me why this is true? Someone can lift their hand and try to give a justification for why this is true. Anybody? Who's okay? Greg, go on.
For every arrow that leaves a node, it must point into some other node.
Right. So another way to say the same thing is that every arrow contributes an in degree of 1 and an out degree of 1, right? So if you have an arrow going from, let's say we have A and we have B, then this arrow here, right? This arrow here contributes 1 to the out degree of A and 1 to the in degree of B, right? So that way, every arrow contributes 1 on this side of the equation and 1 on that side of the equation, right? So if you count up all the edges, then the in degree is going to be nothing but the number of edges, and the out degree is also going to be the number of edges, or rather the sum of in degrees is going to be nothing but the total number of edges in the graph, and the sum of out degrees is also going to be exactly the total number of edges in the graph. And of course, you know, these, since we are referring to the same quantity, that then the equality follows. Okay, so when we have a graph, we can talk about, you know, let's go back to this picture. So yeah, sorry. So this picture. So so when we had you know, this type, when we had that type of a picture, then it's easy to go you know, follow the arrow once, right? So this way we can follow this arrow once. But if you have to follow multiple arrows, it gets a little bit complicated. Whereas here it's very intuitive. You can go, for instance, from A to C, then you can go from C to D and D to E. And not only is it, these steps very easy to see, but in fact, we can intuitively understand, when you can get from one vertex to another, because we have, we can very quickly, looking at the graph, see where the paths in the graph go, right? So so this representation makes it easy to see, where you start and how, where you can go. And essentially what we are doing is that when we go from A to C and then C to D, we are just composing the relation once, right? So, so if you look at this picture, A and D are not connected by the relation, right? But if we compose the relation once, let's call this relation R, right? So we know that A or D is not true. We denote that by just putting a cross through the R, right? We say that A is not related to D, but if we compose R, once over, then we will have A R composed with R D, because if you use the relationship once, then you can go from A to C, and if you use the relationship again, then you can go from C to D. So by going from A through R once and then R twice. Give me a second here. So by using R once here and then using R again, so we can go from A to D, and that's 2 steps are composing R twice. So we introduced a notation last time, which we call as, we defined the notion of R square to refer to R composed with itself. So we can also compose R with itself 3 times, and we will call that R cubed. And can you tell me something that's, let's just, let's make some space here. So can you name an element that A is related to, when you compose R 3 times? Joseph?
Would it be E?
Right, so it is E because, again, you can, if you use the relation once, you go from A to C, you use it one more, you go from C to D, and then you can go from D to E. Okay, so now if I add one more arrow here, right, so that I can go from E to B. Okay, now can you tell me what and you take R to the power 4, then what element would be related to A after 4 steps? Somebody wants to try? Let me have someone else volunteer.
Would it be B?
It'll be B because you go, and then now you can start talking about R to the power 5, right? And that'll take you to C. R to the power 6 will take you to either D or E, and so on. Okay, so now you have a cycle in the graph, so you can keep, how many ever times you apply R, you will still be able to go from A to somewhere.
Quick question.
Yeah.
For r to the power of 4 in this setup,
Yeah.
could it be C if you went A to
Yeah,
C?
you're right.
It could also be C.
Yes, good observation. I should have, mentioned that, but good. So this is why it's important to ask questions, because, I will miss some things which, if I made that comment, that will make it, much clearer for, what we are talking about. So please do speak up. Okay, so let's go back to, where we were. So now let's talk about a walk in a graph. A walk is basically you go from one vertex to the next, to the next, to the next, provided there is an edge between these vertices. Okay, so again, let's go back to our example graph here. So for instance, ACDE is a walk, right? Because you can go from A to C, C to D, D to E. But ABC is not a walk because there is no edge from A to B. So you cannot walk from A to B, right? So a walk is simply, you are taking edges, successive edges, right? And essentially walking through the graph, right? So that's why it's called a walk. So a walk does not have, too many constraints. It just requires that the vertices that you list consecutively in your walk, that there be an edge between them in the right direction, right? So, so we have a sequence of vertices that are part of a walk. And then what we need is we need an edge going from, say, V1 to V2, then V2 to V3, and V3 to V4, and so on, right? So, right, so every VI must be a vertex, obviously, right? And then every pair of successive vertices must have an edge between them going from Vj to Vj plus 1, right? So it shouldn't be the opposite way. Going from, if the edge is from Vj plus 1 to Vj, then that means you are walking in the opposite direction of the edge, and that's not allowed, right? So you have to walk in the direction of the edge. And so that's the notion of a walk, okay? And the length of a walk is simply the number of edges that you have traversed, right? So again, intuitively, we think of walking on the edge, and how many edges you walked on, that is the length of the walk, okay? So we have the notion of a closed walk, which basically says that you start and end in the same place, okay? So a closed walk is a walk with V1 equals Vn, okay? Now, when you're walking, you can go back and forth across the same vertex as many times as you want, okay? But when we say there is a path, then in a path, you are not going over the same vertex more than once, right? So essentially, it's like going from place A to place B. You will use a path to go from place A to place B. But if you just use a walk, that means you are unnecessarily, coming back to the same vertex multiple times, right? So, once again, if you go back to our example, right? So if you take ACE, that would be a path, right? Nothing is being visited twice. So ACE is a path. It is also a walk. ACDE, is it a path or not? ACDE.
Yeah.
Okay, so ACD is a path because no vertex is repeated in this path. Now, of course, every path is a walk, so we don't have to ever ask the question, is this path a walk? Okay. Now, what about ACDEC? Right? Now you are visiting the same vertex C twice, right? ACDEC. So therefore, this is not a path, okay? But it is still a walk, right? Because a walk does not have any constraints on how many times you go through the same vertex, right? Whereas a path says you can go to a vertex, only once, okay? So we can also define, let's not, let me not get ahead of myself here. Okay, so a cycle is a closed walk. Okay, so a closed walk, remember a closed walk says the first and last vertices are the same. Okay, and in addition, we want to Vn minus 1 form a path, right? So a cycle is a walk where exactly one node is visited twice, and that is the first node. Okay, so going back to our graph, so CDEBC is a cycle, right? It starts at C and goes to D, then E, then B, and then C, right? So now you have a cycle. Okay, so is there another cycle in this graph?
Can you start?
Yun? Let's see. Who has, I don't know why this is. Greg?
There is another cycle like CEB.
CEBC. Right, so you're right. Just that the convention is to, list the last node, because if you just say CEB, then that doesn't complete a circuit, right? So you have to go CEBC. Okay, so you start and end at the same place, but otherwise, yeah, there's. Okay, so those are the notions of walk, path, and a cycle. Okay, so there are a couple of interesting observations that we can make. For instance, we can say that the shortest walk between two vertices U and V is a path. Okay, so what that says is that the shortest walk will not visit the same vertex more than once, right? Which is intuitively obvious, because why go back to the same place and then find your way to your destination, right? Because that means you are unnecessarily going back somewhere along the way. So to be and therefore it won't be the shortest walk. So the shortest walk has to be one that never visits the same place twice. So again, when we think about graphs, we have we can relate it to the things that we encounter in our in the real world, such as when you look at a road map or a map of your neighborhood, that kind of looks like a graph with intersections representing vertices and the roads corresponding to edges, right? If you have one-way roads, then you can think of those roads as directed edges. If you don't have one-way roads, then those are like, having either undirected edges or in the way that we have been talking about so far, you can think of them as two edges, back to back, right? So one edge going forward, another edge going backward, right? So we have a sort of a intuitive understanding of graphs, and things like walks and circuits and so on are concepts that we already know from this and understand from this real world experience, and we are just mapping that to this somewhat abstract definition of a graph. And this is part of the reason why graphs are very helpful, because our intuition is very good about graphs. So for instance, when I say shortest walk between two vertices is a path, this is intuitively so obvious to everybody. But if you have to start from first principles and try to prove this, you'll find that it's definitely not a difficult proof, but it's something that's going to take some amount of thinking. Whereas from your real world experience, it's very obvious. If you're walking if you want to go to your friend's place, you'll never come back to the same intersection twice and then assume that you're on your shortest path, right? So again, feel free to rely on this intuition to tell you what the right answer is. But of course, sometimes we ask you to actually show that your answer is correct, then intuition is not enough, right? Okay, good. So, the shortest walk between two vertices is a path, and the shortest closed walk is going to be a cycle, right? Once again, that's quite obvious. Okay, so I won't try to formally prove this, so we'll just take that as obvious for now, and later on come to this. Okay, so once we have a notion of a shortest, once we know what is a path and so on, then we can also define the notion of a shortest path. Okay, because not all paths are created equal. And when we look at our example, it's again becomes obvious. So in here, we have two paths from A to E, right? One path is ACDE, which has 3 edges, and the other path is ACE that has 2 edges. So it's clear that the 2-edge path is shorter than the 3-edge path. So so we can say that the shortest path between A and E has 2 edges, okay? And we refer to this as the distance between A and E, right? So the distance between two vertices in a graph is really the shortest path, or the length of the shortest path between them, okay? And we have this triangle inequality, which basically says the shortest path from U to V, must be less than or equal to the shortest path from U to W, right? So some intermediate node W, and then W to V, right? So if you go from U to W and then W to B, if you put these two together, it cannot be any shorter than the shortest path between U and V, right? This is obvious because if there was a node W through which these two distances will add up to something less than the path you have between U and V, that means that this is actually the shortest path. You should go from U to W and then W to V, and that will be the shortest path, right? So by definition, if you already have a shortest path from U to V, then it should not be possible for you to just pick another intermediate node through which you can walk and then arrive at V in in a smaller number of edges. Okay, and once again, this is something that we know from our real world experience, as well as when we think about properties of triangles. One of the things that we study is that the sum of lengths of two edges is always greater than or equal to the length of the third edge, right? And that's saying something about distances in the real world, and that kind of largely applies in the case of graphs as well. Okay, so let's talk about two types of circuits in a graph. Okay, so Euler circuit is a circuit that visits every edge in the graph exactly once. Okay, a Hamiltonian circuit is kind of similar, but instead of ensuring that every edge is visited once, it ensures that every vertex is visited exactly once. Okay, so let's think of graph. Right, so okay, let's take this graph. Does it have an Euler circuit? Okay, the circuit is a path that or a walk that starts and ends at the same node. Okay, so it's like a cycle, but there are in a cycle you can't visit the same vertex twice, whereas in a circuit you can do that. The only requirement in a circuit is that you start and end in the same place. Okay, so is there an Eulerian circuit in this graph?
Yeah.
Right, you can see it, right?
Yeah.
So you go from so let me just name these B, C, D, and E. So you can go A, B, C, D, C, E, A, right? So you go forward and then come back. So I just drew the graph in such a way that it is very easy to see how to make a circuit. Okay. So what about Hamiltonian circuit? Is there a Hamiltonian circuit?
No.
And the reason for not having a Hamiltonian circuit is what?
You'll eventually have to pass through C twice.
Right. So there's no way to, again, it's intuitively obvious that, if you want to, so the point is that this is like a, choke point, right? C is like a choke point. If you start from one side, then you cannot come back to the same side of C without going through C twice, right? So you start from B, then you go to the other side, which is D. But then in order to come back and finish at B, you need to cross through C again, and therefore there is not going to be a Hamiltonian circuit. Okay, these two notions are very interesting because finding an Eulerian circuit is actually trivial. There is a very simple way to find an Euler circuit, but finding a Hamiltonian circuit is a very hard problem, right? So we talked about, several lectures ago, we talked about the satisfiability problem and said that it is a very hard problem. In particular, we call it as an NP complete problem, which is one of the hardest problems that we know about, right? Same way, Hamiltonian circuit is one of the hardest problems that we know about. In particular, the algorithms that work on, that find Hamiltonian circuits on graphs are generally take time that's exponential in the size of the graph, right? So if you have n vertices, then it's going to take 2 to the power n time to find a Hamiltonian circuit, whereas Euler circuit is can be found in linear time. So is there a question?
Oh, I was just wondering, so a circuit needs to start and end at the same vertex?
Correct.
Okay.
And the difference between a circuit and a cycle is that in a cycle, you cannot revisit the same node except the starting node, right? So you can, in a cycle, you start and end on the same node, but you cannot visit any other node more than once, right? In a circuit, you have to start and end on the same node, but if you go through the same node multiple times, that doesn't matter. Okay. Any other?
Is a circuit the same as a closed walk?
Right. Okay, that's good point. So the circuit is a closed path. Okay. But often, but these two terms, you will typically see then, you won't hear about Hamiltonian closed path, right? So you hear Hamiltonian circuit. So, but yes, but the term that we defined is really a closed walk, and circuit exactly matches the definition. Okay, so there is actually a very simple condition under which an Euler circuit exists, right? And that is that every node, right, at every vertex, right, the degree, both the in degree and out degree are even. Okay, so if they are even, then I'm sorry. No. Right. So the in degree and the out degree should be the same, right? So once you have that, then you can always find an Euler circuit. So let's break here. I'm going to post your next assignment sometime tomorrow. And our plan is to, and it'll be due in about 10 days, right? So maybe not 10 days, maybe. So I'll post it tomorrow. It'll probably be due on next weekend. And we will have the midterm shortly after that, right? So probably in the week after, we will have a midterm. Okay, so the idea is we will go through this, these 3 homeworks that you would have done will be the preparation for that, and I'll also provide a few more sample exams and so on for you to look at, and then after that we'll have your first midterm, and yeah, and before that, as we said, we need to set up some we need, we are going to use lockdown browser, so there will be some practice tests before that, where the purpose is simply to use lockdown browser, not, the tests themselves will there won't be any real content, but it's just a effort to get used to the testing environment, right? And get your equipment set up and so on, right? Okay, great. Let's end here. If there are any questions, I'll be here and you can ask the question. If not, I will see you on Tuesday.
Will there be any other options than lockdown browser? Because last time my school used it, it didn't work for my computer, and I had to do something different.
Well, I don't know what is different from about your machine.
I don't know. Whenever I tried working with lockdown browser on my computer, it kept shutting down.
Well, I'm not sure what to do. Let's talk about it offline.
Okay.
Right. I hope people will have the ability to do this, because I'm not sure that there's the universities. I'm told that there is still a plan to, get a proctoring to work out an arrangement with a company that does proctoring, but then. If I still don't have the information 5 weeks into the semester, I don't know, how to rely on that.
Okay.
But otherwise, so it does look to me that the only option we have at this point is lockdown browser.
Is there an exact date for the midterm?
I will post it again. Everything what I say in class can be easily forgotten, and most of all by me. So I need to make sure that everything is written down. So I'll post it on the course webpage. Okay, and then I'll make an announcement too.
Can you go over the difference between a closed walk and a cycle?
So whatever is there on the webpage, if there is anything, then that is our original plan. Plans change, so those are all tentative dates. So when I post the date now, it'll actually be a firm date. So that's when we'll have the exam.
Professor, I have a question.
Yes, go ahead. I can barely hear you. So maybe you can move closer to the microphone.
Can you hear me now?
Sort of. Let me try increasing my volume more. Yeah. Okay. Go ahead.
Can you go over the difference between a closed walk and a cycle?
So a closed walk, in a cycle, none of the intermediate nodes can be visited more than once. Okay? In a closed walk, you can visit intermediate nodes as many times as you want.
Okay.
So for instance, in this, the Euler circuit that we talked about here, right? That is not a cycle because it visits this vertex C twice, right? So that's not going to be a cycle, right? So we go this way, right? And then we come back. So now we have visited C twice. So that is not a cycle, but it is a circuit, or it is a closed walk.
Okay, thank you.
You're welcome. Anything else? Okay, good. Have a nice weekend, and I'll see you next week.